All right, thanks, Becky. And it's nice to be here. It's pretty far down the street for me to come, and it's a long way, but made it today even though it's snowing. So hopefully it'll be worth your time too for sitting through a little talk I have here. I'm going to talk about some short-lived halocarbons, some chemicals that we're measuring in many of the samples that we're collecting that I haven't typically focused on, but I've had some time lately to pay some attention to. A number of other folks at NOAA and other places that are involved in the work, and there's some people not at NOAA here, Elliot, who was involved in the HIPPO mission, and Steve Wofsy, the head of that HIPPO mission. But a number of these people at NOAA were facilitating collecting samples and making the measurements. And I'm going to be talking about measurements made in the remote atmosphere, different sites from HIPPO, aircraft platforms, other things like that. And there's a bunch of different people around the world, cooperative site partners, who help us facilitate making these measurements. So today I'm going to focus on three chemicals mostly: dibromethane, bromoform, methyl iodide. And these chemicals have pretty short lifetimes compared to the compounds that I'm typically talking about. And their nominal lifetime, and I'll say nominal lifetime because we know that the lifetimes are short enough that their actual lifetime actually depends on where they're emitted. So, but if we just take an OH of 1 × 10⁶ or a photolysis at 5 kilometers at mid-latitudes, we might get dibromethane, we might get a lifetime of a few months. Bromoform maybe 3/4 of a month, and methyl iodide maybe a day. And these chemicals are decomposed by different processes, OH and photolysis. Now, why are we interested in these gases? Perhaps most of you know that the brominated gases may account for up to about 25% of total bromine reaching the stratosphere. There's a certain amount of bromine in the troposphere from methyl bromine and the halons, and when inorganic bromine is measured in the stratosphere, or measurements of inorganic bromine are made in the stratosphere, and a total inorganic bromine in the stratosphere is inferred, it's an amount that's on the order of a few parts per trillion more than what we might expect from the long-lived trace gases. So the thought is that maybe these short-lived gases are contributing bromine to the stratosphere and influencing stratospheric ozone. They also influence tropospheric oxidation processes. They are believed to influence tropospheric ozone, and also for the brominated gases, mercury deposition. They have natural sources, and these sources are thought to be primarily oceanic, and they're present at less than 5 parts per trillion in the background atmosphere. I'll show some more about that in a minute. But I would argue that these influences are not well quantified, influences on ozone and mercury deposition, but also on the stratospheric influence, because of our poor understanding of the sources of these gases, where they're distributed, where those sources are and their magnitudes, and atmospheric distributions, which are an integration of those sources in the loss processes. And so that's where we come in. We're making measurements of these gases at many different sites. And so the questions I'd like to touch upon today are, can we really and reliably measure these gases from flask samples? That's all I'll be talking about today. That's all that I do, is measure compounds from flasks. Can we fill an air sample and analyze it months later and expect there to be the same amount of these chemicals in that flask once we measure it? But more with regard to the science, to what extent can background atmospheric distributions of short-lived gases defined? Is a chemical with a lifetime of a month, nominal lifetime of a month or a few months, does it actually have a background mixing ratio? Or even a week? Can we define patterns in different regions of the atmosphere that actually would suggest, well, we would expect during this time of year that the concentration might be this, like we can for long-lived gases? To what extent can we do this for short-lived gases? And finally, are the data consistent with predominantly oceanic sources? So this is a subset of the locations where we make measurements. And this is a long-lived, well, not long-lived, this is a surface sampling network. We get weekly flasks. We sample these flasks in pairs at these different sites. And I've highlighted those sites in 2 different colors: the low-altitude sites in white and the higher-altitude sites in red. We have Summit and we have Niwot Ridge up here just to the west, and Mount Hualiguan in China. These are kind of interesting because they're very similar altitudes and latitudes, but very different longitudes. We have Mauna Loa and also South Pole. We also get approximately daily flask samples in glass flasks at this suite of tower sites across the US. And most of these tower sites are on the order of 100, well, up to nearly 500 meter tall towers above the ground level. So they're not close to the ground. The inlets are hundreds of meters above the ground typically. There's only one tower where it's 100 meters. The others are 300 to 500 meters. This one in Maine is about 100 meters. And here's a smattering of the results from the background flask network, from the weekly samples. Before I get into the nitty-gritty of whether or not we can make measurements, I thought I'd just tease you a little bit of some of the results that we're getting. So this is a 15 to 20-year record of measurements at just 3 of those sites that I showed a minute ago. Barrow and Alert, the 2 Arctic sites, they're coastal sites in the blue and the red, and the yellow is South Pole. And we're looking at each individual point is a flask measurement, and each individual point is an average of 2 flasks filled simultaneously. And so we can see, as we look at this data, we can see some seasonal patterns emerge. The vertical lines are a year. And we can see some seasonal patterns emerge and some site-to-site differences that persist for dibromomethane, bromoform, and methyl iodide. So maybe patterns over time of time trends of methyl or bromoform, for example, at the blue and red Arctic sites may be increasing over time. Big seasonal changes that are opposite in phase in the northern hemisphere in the red and the blue versus the southern hemisphere. There's 6 months out of phase. And so the question is, can we believe any of these results? And that's what I hope to address first here. Can we make any sense out of any long-term changes? So can we reliably measure these chemicals from flasks? I'm going to talk about accuracy and long-term consistency, precision and reliability, and then show some comparisons with others. And this is GCMS with some accoutrements from my daughter, since replaced. Not my daughter, but the instrument. And here's our NOAA's flask sampling tower at South Pole. And here's at Cape Grim, for example, some stainless steel flasks being filled simultaneously through a pump that's attached to the tower inlet. And these are steel flasks, and we also use glass flasks. So how do we calibrate these measurements? We're talking about Brad Hall in our lab creates standards. He uses pure material and makes a single dilution to create a part per billion level standard. And then he dilutes that down to parts per trillion level in a single step. So it's actually a 2-step process. He minimizes the steps to hopefully minimize errors associated with each one of those dilutions. And these PPT level standards and the other standards define this NOAA scale. Standards are made by Brad Hall with gravimetric techniques from pure reagent and in humidified air in these Essex electropolished stainless steel canisters. These have been a boon for us in making these measurements. These canisters are certified, DOT certified to 900 psi, and typically we use them with enough water so there's near saturation. And that gives us an air sample or a standard that seems to be quite stable over time. We also use treated aluminum cylinders, the Eculife treated cylinders, and we've had some success with those. In fact, most of the reference gases that are used are those types of cylinders. Currently, we've got 2 to 4 standards at the 3 to 20 part per trillion level for each of these compounds, and they were made in 2002 to 2004. And the consistency among these part per trillion level standards is typically within 5%. So Brad can make a suite of standards, come down to a standard at 3 and 10 part per trillion, and the response per PPT that we measure in the GCMS from these standards is within 5%. In other words, if you were to draw a line between the response, you have response versus concentration, it'd be a straight line going through the origin with a variance of about 5% at most. So we use these part per trillion level standards to calibrate a bunch of whole air reference standards. And we do this sequentially in time because it's each one of these standards that we then compare to real air samples over time. So this one is used in 2000, this one is used in 2001, so on. And this is how we generate a scale over time and a reference over time from multiple reference standards used sequentially with some degree of overlap. And each one of these reference standards is then calibrated by comparison to the part per trillion level standards. Over time, new standards get made, hopefully. In this case, we had some that were made in the 1990s, and now we're using the more recent ones. And we can compare those standards together and relative to these the more recent reference gases, decide whether or not there's been any drift in our reference scale over time. So if there isn't any drift in these standards, then we should be fine over time. We should have a constant reference. But we don't know that these standards, that the concentrations of these reactive gases don't change over time. So one thing that we add in addition is archived air samples. We have a suite of samples that we filled at certain times, and we repeatedly analyze these tanks over time to see if we can get the same mixing ratio in that tank. And so I'm going to show you the results of that. Repeat analysis of archived air as a test of our calibration consistency. So if we assume that our standards are stable over time and apply calibration to the reference gases over time, and then with each one of those reference gases measure suites of tanks that are archived samples, this is what we've been able to get. And so this is methyl iodide from 0 to 0.4 part per trillion in these 7 different tanks. 2 of the tanks, actually the concentration in those, they were spiked with methyl iodide and the other gases. So to get them on scale here, I divided the concentration results by a factor of 10. So actually we're looking at about 0.1 ppt in one tank up to about 3 ppt in one of these tanks. And so what we see is that we've been able to assign, based on the fact, assuming that our standards are constant, are stable, we have a suite of tanks that in one of these we've been able to assign a fairly constant mixing ratio over time. The change here, yeah, there might be some increase in there over time, maybe on the order of 10% over this period. It's on the order of a decade. That's what we're able to do at this point. You'll also notice that there's been quite a change in our ability to make the measurement in here. And this is when the old instrument that had the nice diagram from my daughter started to go south. And I went upstairs and grabbed a new instrument that, somebody wasn't looking, and have some nice consistent results since then. So I'm going to be showing a couple different results here where all data plus data since we got this new instrument and have been using it. But for the most part, we have fairly consistent results. We're able to assign or measure a fairly constant mixing ratio for methyl iodide. Also for dibromomethane, now we have results from on the order tanks from 0.6 to now these have been divided by 3, so up to about 3 part per trillion. There are some dips and wiggles in here, and it's hard to know whether or not these are real things associated with drift in reference gases or the calibration scale that we haven't accounted for. But this is the order of magnitude of consistency that we're able to apply for these gases. And this is bromoform. Tanks of at the concentration about 0.3 to 4 part per trillion, or 5 part per trillion. So that gives you an idea of whether or not we're able to assign a consistent scale, and we look at these results and say, well, maybe we can do it over this past decade even, or at least within about plus or minus 10 to 20%. Okay, next thing I want to talk about is how precisely can we make a measurement? And I want to do this because we want to be able to say, if I send out 2 flasks and get them back, I want to be able to answer the question, is there a measurable difference between these flasks? If there's no measurable difference, then there's a good chance that there's been no change in the concentration of these trace gases during the period that they were sampled and transported back to Boulder. And so first we need to look at how well can we make the measurement. And this is a cumulative frequency plot where it's cumulative frequency versus repeat injection precision. And I have 2 lines on here. One's for all the data that we've acquired from flasks, and the other's for after mid-2009. And so this is based on, so to read this graph, 90% of the time when I make two measurements. We've got two flasks, but I also make two injections off of each flask. So 90% of the time, those two injections agreed to within about 17%. Now, we got the new instrument, and it improved. It was more precise. We were able to make that measurement more precisely. It's on the order of 7%. So 90% of the time, two injections agreed to within 7%. And if we look at the other gases, so for the most part, methyl iodide, which I've shown here, dibromomethane, bromoform, two injections agreed to within 10 to 20%. And with the new instrument, we're better. We're on the order of 3 to 7%. And this is that picture again for bromoform. I showed it for methyl iodide previously. This is bromoform. You can see, okay, here's around 10%, and here's around 3%. For 90% of the time, we're able to make that measurement. And let's compare now what we observe as the apparent difference in the flasks that we measure. And that's what we're looking at here. The second line here is that distribution, the cumulative frequency plot of the flask pair difference in percent. And you can see that this flask pair difference line fairly well, it's a little bit to the right, so it's a little bit larger, but fairly well represents the instrument precision. In other words, when we make a measurement of two flasks and we see a difference, most of the time that difference that we see is well described by our ability to make the measurement. So most of those ostensible apparent flask differences are due to the fact that we can't measure with perfect accuracy or perfect precision. So that's looking at all the data. Looking at the data since 2009 with a more precise instrument, we're seeing a little bit of a difference here. So it seems that as we're able to make the measurement more precisely, perhaps we're seeing a little bit of a difference now between the flasks. So that now maybe we can say, well, maybe 80% of the time now, these flasks come back with no measurable difference, where it used to be maybe 90 or 100% of the time. Okay, and I mentioned that we measure, or we use both glass and stainless steel flasks at different sites. And here's an example of something that didn't work very well. And this is methyl iodide at South Pole. Here are a bunch of measurements. Each point is the mean of a flask pair. And these error bars represent the standard deviation associated with the two flasks. And we can see that here's a result right here where the standard deviation, the flasks were different by an awful lot more than 20%, different by factors of 2 or 10 even. And so you look at this record and you go, this looks to be just nonsense. It's hard to make much sense out of it. Mostly you can look at that and understand that just by the fact that because we have two flasks that we filled simultaneously, made measurements. But fortunately, we also collected, so South Pole, why is it difficult? Well, the air is extremely dry at South Pole, and also the air is stored up to 10 months before we analyze that in these steel flasks. We send a suite of flasks down there. The pole closes at February. Nothing moves in and out between February and the end of October. And so we have people down there fill the flasks up for us. The ones filled in February don't get analyzed until November or December. So the air sits, that dry air sits in that stainless steel flask for extended periods of time. Lots of chemicals degrade in that flask. So that's why we also send glass flasks down there. And we see the red results from the glass flask. I'll get rid of the stainless steel flask. And we can begin to see a regular seasonal cycle. These lines here and the peaks in this record now are repeatable annual changes. And if I plot that as a function of time, fraction of year, methyl iodide, the red points are the results from the flasks. And this is the night period as sun rises and sets once each year at South Pole. We get a nice, fairly repeatable pattern. There's still some glass flask results that are down here. I don't understand those. But you can see that we get a much different picture and a more consistent picture from the glass flasks than we do from the stainless steel flasks. And I think this glass flask record is a much more reliable record. In fact, when we look at the results that we get from Summit, they're very comparable to what we get at South Pole for methyl iodide, just 6 months shifted. Summit being northern hemisphere, also high altitude, very cold, high latitude site. So at other sites, stainless steel and glass flasks give fairly similar result. I have plotted here for dibromomethane we measure this Wisconsin site daily flasks, come back to Boulder for measurements, and we have each one of these points is a monthly mean over the past 6 years. And monthly means from the daily glass flasks are in blue, and from the weekly stainless steel flasks, the monthly mean from those are in red. And you can see a fairly consistent pattern here. There are some differences, no doubt, but from either the stainless steel or glass, you would derive an annual mean that's fairly similar, and you get a picture of the seasonality from both of these sites, or from both of these different means of making the measurement. And this is actually a little bit surprising, given the fact that we're comparing daily samples over a month versus weekly samples over a month, and we get this similar pattern. If there's lots of variability in the atmosphere for this chemical, you would expect that this picture wouldn't even be observed, even if the flasks were behaving well in both instances. Here's the picture for bromoform. Also, I would say fairly consistent results for the daily glass flasks and for the weekly stainless steel flasks. And also for methyl iodide. We see some periods where there seem to be some differences. Maybe it's not surprising, given that we're talking about methyl iodide. It's more variable in the atmosphere, and we're capturing more of that with the daily samples. But the annual average here and the variability seasonally is similarly captured by both measurements. Okay, and finally, making comparisons to others. This is a sample-to-sample comparison to in situ measurements at a subset of the sites and a suite of sites of their own. The A-gauge community makes measurements, and they make measurements with GCMS, but a GCMS that's on site at that location. And Paul Crumo is kind enough he goes through this data regularly to pull out the flask measurement and pull out of the in situ record a measurement that was made at a similar time to when that flask measurement was sampled. And his match time is plus or minus 3 hours. And so from that, we get a comparison of an in situ measurement versus the flask measurement for bromoform, for dibromomethane, and for methyl iodide. The correlation coefficients here are on the order of 0.6 to 0.8. Now, the fact that they're centered around the one-to-one line isn't important here, because actually they use the NOAA calibration. We've transferred the NOAA calibration to the A gauge. But the fact that we get a reasonably high correlation coefficient suggests that we're both capturing similar variations from the in situ instrument and from the flask instrument, despite this match time this fairly broad match time. The fact that a flask sample can be measured at one time, and 3 hours later an in situ measurement could be made, and that's what's being compared here, up to a 3-hour difference in those air samples. Okay, so I hope I've convinced you that we think we have a fairly consistent reference gas over time, within plus or minus 10 to 20% over the past decade. The flask pair differences are fairly well described by instrumental imprecision. The results from stainless steel and glass flasks agree quite well at most sites, but not all. For example, South Pole. But because we measure in pairs and different types of flasks, we're able to detect when things go awry, when things go wrong, when things go awry. And so hopefully the resulting data set that we have is more robust. And we've made some comparisons to in situ results that give fairly good consistency, show fairly good consistency. So back to this surface network. Daily flask samples. The next thing I want to talk about are annual means at these different sites. Let's just look and see what are the annual mean mixing ratios that we measure at these different sites. And we're first going to talk about dibromomethane, and we're having parts per trillion, 0 to 1.5 part per trillion. And I've colored, and this is from the minus 90 South Pole to the North Pole. And I've colored these results by altitude. Low altitude sites are in white, the high altitude sites are in red. And the error bars here, I hope you can see them, maybe you can't see them. You can't see them in the red because they're smaller than the size of the symbol, represent the one standard deviation of the yearly means. We get a yearly mean mixing ratio for dibromomethane in 2000, 2001, 2002. We average up those, I think it was approximately, at some of these sites, 15 annual means, take a standard deviation, and that's what that vertical bar represents. And you can see, so even though this is a fairly short-lived gas, year after year, we've actually measured the same, just about the same mixing ratio. There's very little interannual variability in the annual mean mixing ratio at these sites. even when we capture them just with a weekly flask. So the atmosphere is pretty consistent in terms of its distribution of dibromomethane. But there are fairly large site-to-site differences. There are differences in the environment at each one of these sites. But what appears most consistent to me, though, is that there's large site-to-site difference, but except at high altitudes. These 2 points here, one is Niwot Ridge, and this is Mount Hualiguan, China. So 2 different continents, high altitude, free tropospheric samples, we get about the same annual mean mixing ratio. The one caveat on this is that Mount Hualiguan, we've only made measurements there for 2 years, whereas for Niwot Ridge, we've made measurements for over 10 years. But we have results at Summit up here, these mid-latitude sites, and Mauna Loa, and then South Pole over here. This pattern right here is almost reminiscent of almost what you might expect for a short-lived gas, where there is less at lower mixing ratios towards the equator because of higher loss rates. How about bromoform? Similar pattern exists, where annual means and their standard deviation over time are fairly small at the sites that are free tropospheric sites, and we see a similar pattern: higher concentration at the poles, lower concentrations toward the equator, perhaps. One could interpret this. And the low altitude sites, much more variability. But fairly high consistency from year to year at all of these sites in the annual mean mixing ratio that we derive from the weekly measurements that we've been able to make. And this is methyl iodide. Methyl iodide shorter, has a shorter lifetime, things look a little bit different. Mount Hualiguan, for example, isn't similar to Niwot Ridge anymore. We also have these free tropospheric sites, even though they're at the surface, they're showing very consistent mixing ratio. And we also have the low altitude surface sites showing consistency, fairly good consistency, fairly high consistency from year to year, but more variability from one site to the other, presumably because of the local environment being different. I mentioned also that we have these different tower sites where we get a daily flash sample. I plotted those points on here. They're a little hard to see, but in yellow. And they pretty much don't change the picture. Over the continent, we see slightly higher concentrations, some scatter in the results that we get, but no more scatter. Some of them are coastal sites. Some of them are interior continent sites. None of them are high altitude sites. None of them are sampling the free troposphere, so it fits in nicely with the other data that we're seeing. But measurements on a daily basis from a different type of flask, just glass flask. The other results are glass flask and stainless.
Is the bromoform outlier there by sites?
Mace Head. Yep, this is Mace Head, which is that's probably where most of the measurements of bromoform in the world have been made. Yeah. Okay, the other platform where measurements are made are from aircraft. So since about 2004, mostly I've been making measurements since 2007. There's a number of different sites around the world, even in China and Southern Hemisphere too, but mostly focused on North America, where we get regular profiles from aircraft. Usually 12 flasks are filled, not in pairs, but singly, up as the plane cycles or flies from 8 kilometers back down to the surface. So we have records now of the atmosphere in altitude dimension at these sites, long-term records of these that I'd also like to add to this. And in addition, we were involved in the HIPPO mission. And so we can begin to look at those results too, since they're characterizing the free troposphere and the boundary layer over the Pacific Basin. So what I hope to do next, part of what I hope to do next is what are we getting in the free troposphere over North America and for these different gases, and how does it compare to the free troposphere over the Pacific Ocean Basin? They're short-lived gases, they're influenced potentially by local sources, but if we look in the free troposphere, is there a degree of consistency in what we see over over the continent versus over the Pacific Ocean? The HIPPO measurements combined with this aircraft campaign allow us to do that. Here's an example of the sample distribution. And this is for 1 month in November 2009. This was one of the HIPPO. This was during one of the HIPPO missions. So the blue points are where it's altitude versus latitude. Blue points is where the HIPPO flasks were sampled. And so fairly good distribution, flying down and back, mostly in the mid-Pacific Ocean. The green points are the ongoing aircraft profiling flasks that were collected during that month. And if things work out, during every month. It doesn't always work out. And on top of that, then, are these red points are the surface sites. So the free tropospheric surface sites that I've been talking about recently. And then here are the tower sites, and here in the gold triangles. And then the yellow circles here are the surface sites, how they're distributed. So here's a picture of the measurements that we made during this 1 month. And now we're going to compare the green points, the distributions from all these different measurements as a function of latitude for these different chemicals. And we're first going to look at the results that are in the free troposphere. The red points are those surface sites that are high altitude. The green points are the results from the aircraft, the ongoing aircraft profiling missions. And the blue points are from HIPPO flasks at 1.5 to 8 kilometers. And I've made 4 panels here, different seasonal periods. This is the spring, Northern Hemisphere springtime. There's 2 HIPPO missions combined into this. Here's June, here's August, and here's November. Is that right? That might not be right, actually. This might just be the one, and I've left one out. But here's dibromomethane in the free troposphere in different months. We first look in the springtime, and we see perhaps there's higher mixing ratio. Well, there is higher mixing ratios in the Northern Hemisphere than in the Southern Hemisphere. Not very surprising, given if we consider that that this chemical is destroyed primarily by OH. It could be that, given that this is just the Northern Hemisphere just coming out of the winter, we might expect higher mixing ratios in the North and the South. As we move to the summertime, we see that the situation's reversed. The Northern Hemisphere mixing ratios in all these different measurements of the free troposphere are lower than what we observe in the Southern Hemisphere. We go into this later in the summer, the picture persists, and then into the fall, we see the Northern Hemisphere coming back up relative to the South. I forgot the primary point. The first point, looking at this figure, is that you can look at the HIPPO results over the Pacific Ocean basin in blue, compare those to the green points, which are over primarily the continent, and see that you get a consistent mixing ratio, dibromomethane, if you're looking over the continent in the free troposphere, or if you're looking over the Pacific Ocean basin. So it seems like the lifetime, and what you're getting from season to season are variations that really look to be consistent, at least qualitatively, to the influence of the seasonally varying source rather than seasonally varying, the seasonally varying sink rather than seasonally varying sources. The pattern looks to be responding to changes in the sink, not to any local sources or changes in sources. What if we look just briefly at low altitude sites then? What do we see if we look at the measurements over the continent and the results from HIPPO at low altitudes? We see higher mixing ratios, especially during the summer in the boundary layer. We see periods where the yellow points now are the HIPPO flasks, the HIPPO samples, but within the marine boundary layer. All the yellow points are low altitude measurements overlaid on what I just showed you. And the big circles are the surface sites, and the smaller yellow points are flask samples taken from the HIPPO mission. So you can see times where low altitude samples, Samoa, or low altitude sites, Samoa and low altitude samples taken from the HIPPO mission agree quite well with the higher altitude samples. And there are other regions where there's some differences between what measured in the boundary layer and what's being measured in the free troposphere. Those differences are fairly noticeable, or become more noticeable in the summertime over the continent, for example, here and also here in August. and less so here in November. So when I look at that, I see what looks to be a consistent seasonal change in the background mixing ratio of dibromomethane in the free troposphere. And I showed HIPPO versus continental measurements. And now let's just focus on what that was 4 to 5 snapshots. Now we're making regular measurements from the terrestrial aircraft sites. And this is what those results look like, plotted as a fraction of year for these different sites. And you can see that it's even more clear that each one of these sites have Alaska, Saskatchewan, Wisconsin, Vancouver on the coast, Colorado, New Hampshire, Trinidad Head, Gulf of Mexico, and South Carolina. In the free troposphere, above 4 kilometers above sea level, we see a regular seasonal cycle variation. And the mixing ratios at all these different sites is quite comparable. So it seems like there's a broad scale variation in the free troposphere and mixing ratio of this gas. And on some of these panels, I've shown some blue lines that are results from a surface site to look at comparability, to see like we're measuring at above 4 kilometers at Alaska. How does it compare to what we're measuring at Summit, which the altitude is, I can't remember right now, 2,500, 3,000 meters above sea level? Does anybody know for sure? Very comparable mixing ratios at both of these different locations. Here I'm comparing the results from above 4 kilometers to what we're getting from the tall tower, which is only 400 meters above the surface. And we see quite comparable results, even though we're looking at the surface measurement from the tall tower compared to above 4 kilometers. Very consistent, suggesting that there's not large sources within the marine boundary layer at this location. We have results from Colorado out here east versus Niwot Ridge here, and Harvard Forest versus flights over New Hampshire, and Trinidad Head off the coast of California. Here we see a difference in summertime, suggesting that the surface site is impacted substantially and regularly by emissions in the marine boundary layer. We have some rather unique sites that I just want to add here, and this is Rarotonga, the Mongolian site, and Hawaii. And the Rarotonga site's in the southern hemisphere. What do we see? We see the seasonality has an opposite phase. And what I've shown here in blue is what the seasonality and the results from Samoa. And here we have Mongolia, very consistent with Niwot Ridge in its annual mean. I showed that a bit ago, and now we have consistency in its seasonal cycle too. And this was Hawaii results, fairly consistent with what we're observing at the surface. And I have 2 lines here. One's the top of the Mauna Loa volcano, and the other one's on the coast, Kumakahi. Okay, and these are the results. The yellow points now have been added on top of that. The scale's been adjusted a little bit to look at what we're observing from the aircraft, from this aircraft profiling network, from the aircraft within the continental or marine boundary layer. And you can see examples of enhancements that are yellow points. I hope you can see that. Particularly off the coast of Vancouver, for example, in the Gulf of Mexico, but also South Carolina here. Maybe here in the fall of New Hampshire. And some indication of this surface-based source off of Trinidad Head. So perhaps some indication here of where the sources are for this chemical. Now we can look at bromoform. Here are the measurements for bromoform. Back again, comparing HIPPO to the surface results to the ongoing NOAA aircraft program. And we can see that the seasonality is the picture of, well, number one, consistency. There's a lot more scatter in the results. These low samples here probably have to do with influence from the stratosphere. But there's still similar mixing ratios in the free troposphere over the North American continent and the Pacific Ocean basin during these different periods, from springtime, northern hemisphere, summertime, northern hemisphere, August, we're getting more scatter in here, but back into November, both over the continent and over the Pacific Ocean basin, we're seeing enhancements in the northern hemisphere compared to the southern hemisphere. Also, the same pattern, so we have some consistency again here, less so for bromoform, perhaps because it's lifetime shorter, well, most likely because it's lifetime shorter. but also some patterns that also reflect changes, I would think, in the seasonal cycle of the sink magnitude, where we have southern higher than northern here in the northern hemispheric summer. Doesn't really persist here. Now we have more samples, high samples here in the summer, but when we get into the winter season, we get back higher in the north versus the south. All right, I'm going to change the scale a little bit and then add results from the lower altitude sampling sites. Mace Head here, Cape Grim here, Palmer Station here. Similar picture, but now even larger enhancements in the boundary layer samples for bromoform, reflecting what looks to be surface-based sources. And the differences seem to be largest during the summertime. Right here and right here, perhaps, for this chemical. And this is bromoform from the aircraft profiling locations. So the previous was just a snapshot of 4 different seasonal pictures. Here's the ongoing measurements at these different locations, mostly over North America. And we can see these are all free troposphere for bromoform now. Same suite of sites. We see a regular seasonal pattern. The seasonal pattern becomes more obvious when we look in the free troposphere on a monthly to weekly basis from these aircraft profiles. And we see that the concentrations are fairly similar. We do see, though, that the concentrations in the winter time in the higher latitude locations get to higher concentrations than at the lower latitude sites, the Gulf of Mexico and South Carolina. The high here is maybe 3/4 parts per trillion, where the high up here during this season might be 1 part per trillion. That makes sense with respect to the magnitude of the sink processes and how that varies. Yeah. That's right, yeah, and that's why they're plotted on here. In the free troposphere, the picture isn't much different than the other sites at Trinidad Head, but in the surface, we see evidence for much different, much higher mixing ratios, indicative, here's a site where there's likely large local influences. We don't see that so much at Summit, although there's some interesting differences between what we're measuring over Alaska versus over Summit. This comparison is, if you remember, Wisconsin was the tall tower, but it's only at 400 meters above the surface, and these are 4 kilometers above the surface or more, and we're seeing a little bit of a difference there, and also at Harvard Forest. This is Niwot Ridge and the Colorado aircraft profile sites are quite comparable. And here's, once again, the unique sites, Rarotonga, Mongolia, and Hawaii. Not much to add there other than there's somewhat of an opposite seasonality here, perhaps, in the free troposphere, maybe because of sinks. And for Hawaii, for bromoform, we see quite some difference now between one of these sites, one of these ground-based sites, and the free tropospheric results. And this ground-based site is the one that's within the marine boundary layer at sea level. This is the Mauna Loa result here in blue. So the high altitude site agrees with the aircraft results and a quite low mixing ratio, but down low in the marine boundary layer, we're getting enhancements throughout the season. Okay, and here's same picture now, but with overlay. The yellow points are within the low altitude, less than 1,000 meters from aircraft. And we see large enhancements in Vancouver, over the Gulf of Mexico, in South Carolina, also in New Hampshire, maybe some enhancements here in Wisconsin during the fall, and with Saskatchewan during the late summer and fall. And this is an interesting question of whether or not these are enhancements because of local sources or because of, these enhancements being transported in from somewhere else. And we can see these enhancements in Trinidad Head, like Sherry mentioned. Okay, and then let's move to methyl iodide quickly. Methyl iodide, a little different picture than the other gases, shorter lived, but not, low. What to say about this comparison? We're getting down to very low concentrations. So, I could say that these are very consistent, and yet these 2 points might be a factor of 10 different, but small in terms of concentration. And we also don't see so much this seasonal variability in moving from one season to the next. There may be a hint of it here in the northern hemispheric summer. There may be a hint of it here in the northern hemispheric winter, slightly higher here than in the southern hemisphere. I did show before the South Pole record for methyl iodide, how that had a very nice seasonal cycle, high in the wintertime and low during the summer, with a peak about half a part per trillion, and that's what we're seeing here. And when we add on the low altitude sites, we get this picture, which for the most part looks like variable mixing annual or variable monthly mixing ratios at the different sites, more influenced by regional or local sources. But we also the highest concentrations are observed during the summertime over at low altitude sites, and some of these locations are not coastal sites; they're continental sites. If we look at the ongoing record, we can see some seasonal patterns at the higher latitude sites, Alaska and Wisconsin. But that pattern becomes less as we go to lower latitudes, more towards the equator. And we see instances of certainly what looks to be local source influences. These sites, local influences at Rarotonga that we didn't see before, perhaps for Rarotonga versus Samoa. And this Hawaii picture looks similar as it did to bromoform. Evidence for potentially sources in the marine boundary layer of methyl iodide around Hawaii. And here's the picture now of the aircraft measurements. Now overlaid the low altitude measurements. And the biggest thing I want to point out about this is that we can see, like at Saskatchewan, we see that the low altitude sites follow, the lower manifold of those data follow the free troposphere fairly nicely. But at Saskatchewan, we have enhancements here and there. At Wisconsin, we have similar situation where we get even the marine, or even the continental bound. Remember, this is in Wisconsin. The continental, I'll try to remember, the continental measurements in the continental boundary layer follow the free troposphere fairly closely, except for during the summertime. There's enhancements in the continental boundary layer for methyl iodide. That picture is also seen once in a while, even in Colorado, slightly east of here. But for most of these sites, we have some seasonal pattern of behavior with enhancements over the summertime. Over the Gulf of Mexico, we see enhancements pretty much all the time, maybe enhanced during summer. South Carolina, it's hard to know whether or not this is a marine or continental influence. Trinidad had most certainly is I would guess, and Vancouver, I would guess, is mostly a marine influence. So those results for methyl iodide show the potential for an influence of a terrestrial-based emission. And I just wanted to show this figure. I think it's my last figure here. This is methyl iodide from terrestrial sites. So we have this tall tower network. Daily flasks are collected. And I've shown now the results for methyl iodide in those towers. And this is Wisconsin, Maine, Iowa, California, near the coast. Well, actually, it's in the Sacramento Valley, Colorado, and Texas. And these are the results for methyl iodide. And these numbers here are the sampling altitude above the surface. So we're not right next to the surface. We're fairly high above the surface in some instances. And this is what we see for methyl iodide. We see this seasonal variation, like I mentioned, and like we saw at some of the, particularly higher latitude sites in the free troposphere. But we see all these enhancements during the summertime. They're not visible and not present there in the wintertime, but in the summer we see these enhancements. And because we're seeing Wisconsin, Colorado, and Iowa, it really seems like this is a terrestrial source for methyl iodide. We see these, the picture's a little different at Texas, but certainly we have some Gulf flow influence here. In California, certainly we have influence from the coastal region, and I can imagine that we also do at Maine. So just to summarize then, I hope I've convinced you that this ongoing flash sampling program that we have at NOAA, and also short-term projects like HIPPO, allow us to characterize variability of, in this instance, these short-lived gases over latitudes, longitudes, and altitudes in a way that perhaps we weren't able to beforehand. And I think the observations show consistent mean mixing ratios from year to year for all three of these gases at a wide range of sites, but typically large site-to-site differences. But there's fairly higher consistency site to site when we start to look in the free troposphere. And the seasonal variations seem to be driven, at least if I look at it qualitatively, they're consistent with those variations being driven primarily by losses, especially for dibromomethane and perhaps for bromoform. Methyl iodide, with a shorter lifetime, exhibits a higher variability, no surprise. And perhaps we can begin to characterize a true background concentration of dibromomethane, for example, and maybe even bromoform. We've seen boundary layer mixing ratio enhancements above land and sea whose magnitudes vary seasonally, and it really looks like we're seeing some evidence of a terrestrial methyl iodide source. And for these short-lived gases, the free, if we step back just a little bit and say, this free tropospheric data, I think, provide an important context that allow an assessment of the distribution and seasonality of sources. When we look at a place where we see enhancements above what we're measuring in the free troposphere, it really indicates that there must be some regional source nearby that's influencing these measurements. And